이렇게.
Also, sorry about the screen question. Okay, so today I'm going to review some sort of technology for this classification, which was published in 2014. And first, let's see what is software spectrum machine. So software spectrum machine is kind of a supervised measurement algorithm. So what's a supervised measurement? So we have a data set that model that test and we want to classify the new picture, that is a picture of a cat or a picture of dog. So here we see the motion neural network that extract features out of the each data with each picture. So at the end we can classify which is which. So let's simplify the problem and let's consider the easy case. So we have a data set and we have a model of red circle and green and cross. So you want to classify the new data. So the easiest way is to draw line between two groups, right? And the best line would be in the middle of these two things. Just one line marker. Okay, so this plane is obviously the optimal. Okay, so we want to find this plane. And
I'm sorry.
we should set up an optimization problem.
Hello.
So let's
hello.
This part is the inverse distance, inverse of scalar module, which you want to maximize. And C is error that the data is away from this well, some might prefer to solve this constraint optimization problem directly, but it's actually easier to use strong reality and change the problem. So this dual form is equivalent to trinomial form if this next optimized. And as you can see, we have only one variable, which is Lagrangian, known as Lagrangian multiplier. Yeah. So the biggest advantage of this kind of method is you have only one vector variable. I mean the one variable vector, and the only thing we need to pre-compute is the inner product between data. So in Harmon form, you want to get optimal W, which is a plane vector. E is bias and as well as error. By the way, these two equations are equal. So this is much more, in a way, harder because we don't know W, and we have to evaluate this inner product every time we update W and B. So yeah, your form is easy. So if we solve this problem, we get the corresponding pipeline and equation for classification, which is very simple. So what about the nonlinear case? Here, data are you can't draw a line, right? you can draw a line that separates two red and blue. That's perfect. And you have to draw a curve, but this problem can be solved if we map the data into higher dimensions. Like this. So this is a feature space, and in feature space you can draw a hyperplane that separates two classes. So that kind of mapping is called feature map. And if you define inner product of map data, yeah, a corner is the inner product of two map data. So yeah, a corner is yeah, inner product in feature space. So we can define corner like this. And there is a theorem that for positive semi-definite corner, we all know what is positive semi-definite, right? Yeah. Think about this method. So positive semi-definite corner, if there, then there is a unique unique feature. So we just set corner and we automatically it's like we automatically set feature. So answer, which one would be easier to solve? Okay. Obviously, the one, the lower one, because color is just a function from n-dimensional space, and feature map is a function from n-dimensional space to higher dimension. So it's really hard to choose the best color function. But here, can just use value function. Right? So for example, you can think about function. Here, RDF means regular-based function, which is essentially function. Function is part of RDF function. So this is like a inverse of distance. So or maybe similarity. So if it is similar to, they're more likely to be in the same side of hyperplane. So yeah, you can do this kind of nonlinear classification if you use Common tree. Yeah, this kind of method is called Common tree. Yeah. So then let's go further. So in this paper, this paper, they use different kind of SPM, which is called least square SPM. So equation is given like this. The difference is that in usual SPM, you have an error here, and error should be positive. But in least square SPM, you have a square of some kind of error, which is given like this. Yeah. So this is the equality constant. And as you can see in the figures, can you see the difference? So in LSS, then it is desirable to have all the data aligned with the constraint. But in SPM, data should be apart. Yeah. So that's the difference. And this small difference leads to huge convenience, because this is the Euro form of SPM. You can see we have a quadratic term. So we need quadratic programming to optimize it. Actually, if you change this equation into zero form, it's linear equation. So yeah, if we solve this equation, which is very easy and exact, we have a optimal beta B and alpha. Yeah, so essentially we need to solve this equation. Then we have optimal Yeah, as you can see here, this also uses K, which is corner metric, corner value of training data set. So yeah, this is also a corner-based algorithm. Regularly. So we need to get corner metric, right? And one way to do it, actually the only way, I mean, it is not only that, if you consider mathematical, you have to use QRAM to make a metric. So, you guys know what is QRAM? So QRAM is like a RAM that is quantum. Okay, so this is how it works. So we input some we have some register qubit, and in with that register qubit, we have some data stored, and it's all in a superposition transfer. So for example, if you want to get ice data, we input 0 and we get the 0, and we can input superposed index, and we get the superposed output. Yeah, basically that. So we input all all index in a uniformly superposed state, then we get this output. So we have a ice data, and it's all because the side of x is not all equal, so we have some kind of amplitude difference, but yeah, all the outcome is equal. And the color metric, which is normalized version of actual color metric, we can get it from tracing out the data. And like this. So as you can see, this is column. This is so inner product value, and next, okay. Yeah. And as I will explain in later slide, we actually need to make the exponent of this color metric. So let's assume color metric is not sparse, so rank is almost full. And this technique is actually introduced in differentiate before. I think someone reviewed it, right? Not in this room. So we want to make this kind of evolution on the dynamic. So this would be meter metrics. And it is known that these are similar to square order delta t, I guess. Yeah, I'm a little bit fuzzy on this one, but yeah, they're very similar. And what is that? X is just a swap, global swap metric. So this is easy because we know every component on this metric. So we can make this kind of evolution possible. It is very easy to implement in actual quantum circuit. And this part means that there's a tensor product between corner and some arbitrary input group. So in the circuit form, K here, rho here, and go global swap and trace out this one. Yeah, in this way we can actually implement U or quantum phase estimation why do we need quantum phase expansion? Because we need to inverse the matrix that are available to find. Okay, but actual equation we need to solve is this one. Right? So it's little bit that's k, but little bit different. But it doesn't matter because J, which is just this matrix, and identity is well known. So you can make a literally like this. This is trivial, and this has only it has known that it has only two eigenvalues. So yeah, this part and this part. So we need to get this part, which we did in the last class, and the difference is some order one component. We can just tune delta t to this type. Yeah, so we make a econometric exponential. Yes, an econometric exponential. And now it's time for econometric inversion. We can just use HHA algorithm. This paper. So funny thing about this is it's actually linear solver algorithm, but people call HHL because Harold has been and Boyd. So first letter of their name. Okay, I'm not going into details about HHA algorithm, but I will briefly explain. So there's this kind of equation, and HHA gives the solution. So we first assume that eigenvalues of A or 1, A has to be a Hamiltonian. Yeah, in general, A has to be Hamiltonian. And eigenvalue is in between 1 and 1 over half. We have this kind of circuit, so we use QPE. So we get matrix, quantum matrix exponent, and we just input that in this QPE, and it gives eigenvalue, and depending on that stored eigenvalue, we can do an eigenvalue inversion. And also QPE, and then we have if circuit is if this measurement is successful, then we have this optimal normalization factor. And it is known that the order is log n, which is the dimension of A matrix. In this case, we have n is number of frame data in the data set. F matrix was. Okay, so I really advise you to look into this link. This is part of the Qiskit textbook that explains HHA algorithm in detail. And there's a code, and this is really well written. So I advise you to look around that. Okay, so we have a solution. Solution in this one. So, well, we have solution so that classify new data. So new data is I write it as x hat, and if you query current with the solution, we have this vector, like this thing. So if we do Hadamard test, which is in this, we get this equation. So this is actually same as time vector times data. Yeah. I think I need to explain this more in context of KKT condition and etc. Well, yeah, I'm sorry that I missed that kind of explanation. And we can see this as a corner. Actually, this whole as a corner. So corner times yeah, I think this is the solution of KKP conditioning strong theory. So anyway, you can just Fourier theorem with the solution in the inverse solution of HHJ algorithm and your inner product with obviously amplitude encode data and we have estimated lambda, so we can specify the concept. So what's important about this algorithm is that it's very fast in terms of data set. So Turing, which we need for econometric, we can actually get econometric in order of log mn, given that Turing is already existing. And the extra part like phase estimation, metric exponentiation, that's including all that we have a total runtime distribution. So order in terms of m and n doesn't change. So it's logarithmic model. Whereas in classical or general non-sparse econometric, they're actually cubic to the n or in sometimes square root of n. Anyway, it's cubic or square root. So it's much more faster. Logarithmic and so we have some advantage. Okay, so up to now we just consider amplitude encoding, which is linear SPM. And we also make non-linear. That this is just tensor product of the copy of data, and we have this kind of column. So this is polynomial column. And actually, calculating this inner product is very, very efficient in quantum. So the tree is also logarithmic order, but in classical or polynomial order. So calculating polynomial order itself has a quantum. Okay, so visual feature. To do QSDM algorithm, we don't actually need the data itself. We just need econometric. So let's say we have a client and server. The client just need to provide econometric testing metrics from then server can solve the problem and give it to client. So yeah, data is secure. Yeah, and that's all great. So let's have some discussion. So this is my personal opinion. I think the strength of this QSML algorithm is obviously exponential quantum speed with logarithmic order and very good example of showing quantum advantage. But in practical, let's just say there's no truth that shows logarithmic Fourier quantum. So there is a polynomial or linearly linear runtime QRAM, but as far as I know, I don't know any QRAM that shows global. Yeah, and also there is a few contact components like matrix exponent, JS, and HHR. So that's yeah. So it's really hard to actually implement this algorithm. Yeah. Yeah, and also another strength is, as I said before, calculating inner product in custom meters is easy, so we can make a color function flexible in Fluent. So using that kind of feature, there is another paper from IBM. You should check this paper too. So it's not really related to this paper, but it uses feature space, convenient feature space to specify data, and that is the way they did it is really closely connected to SVN primal form. And another strength is they claim another strength is data privacy. But let's think about it. If we have a color matrix, can you extract information from it? Yeah, I mean, not perfect, not all the information, not all data, but I heard that when you have a trained neural network, you can actually extract data used for that, used to train that neural network. So, yeah, data privacy, I don't know. That's trying to learn more about that, but I think the data privacy data is perfectly safe. Okay, so that's the end of my presentation. And do you have a question or some misunderstanding?
What I remember from your presentation, you said that in order to show the matrix you want to invert needs to be Hamiltonian.
Yeah.
Yeah. So in this case, in the TSN case, is the F matrix only permission?
So graph is given like this. As you can see, color is actually it's symmetric, but symmetric is larger. Yeah, so it's always density. It's density metric, so it's always.
I was just wondering.
No, it's not permission. Color is permission. Yeah.
And also for the time evolution of test is you said it was easy to implement, but I didn't quite understand why.
Well, because as every so and as itself is very sparse. I think it's ranked 1. Yeah, so it's making it's gonna offset it also. So any further questions? So, one remark about HHL is that this register is actually for recording eigenvalues of A. We only account case estimation ID. Yeah, so we actually need many qubits to very small error for that is reflected in the qubit of error. We don't have any more questions. That's this one.